All right, our goal is to set up an exponential function, an exponential equation that models the Gangnam style music video. And we've got a couple of data points to work with. Um, we're told that we should use T as days after this video has been uploaded to YouTube. And we know that after 15 days, there were 15 million views. And after 40 days, there were 70 million views. So we use T as the number of days after it was uploaded, and A should be the amount of views in millions. So we've got two data points. We just fill in our equation with those numbers. And then we have two equations that both involve A naught, the initial amount, and the rate R. We don't know either one of those. Notice it's a little weird to be doing this and not using A naught equals 0, because A naught is supposed to be the initial number of views. But we get a more accurate model if we don't use A naught equals 0. In fact, if we use A naught equals 0, then there's no model. It just says the amount equals 0. So it doesn't work if we use A naught equals 0. And I don't have the amount for after the first day. So we're just going to use these two data points. We'll solve for A naught in both equations and then set the two equations equal to each other. So just divide that first equation by 1 plus r to the 15th, and by the second one by 1 plus r to the 40th. That solves for A naught in both equations. Then A naught has to be equal to A naught, so you set the right side of both of those equations equal to each other. That gives you one equation with one variable r, so you want to solve for r after that. And you can solve for r by first getting rid of the denominators. So I'm going to first multiply both sides of the equation by 1 plus r to the 40th. And when I multiply the right side of the equation by 1 plus r to the 40th, I just get 70. But when I multiply the left side by 1 plus r to the 40th, I've got a 1 plus r on the top and a 1 plus r on the bottom. So I just subtract the exponents. 40 minus 15 gives me 25. So I get this equation. Now I know how to get rid of that 25th power. You just raise both sides to the 1 over 25. First, I'll divide both sides by 15 to clean it up a little bit. Then when I take the 25th root, I just get 1 plus r on the left. On the right, after I reduce that fraction, it's 14 over 3. So I get 14 over 3 to the 1 over 25 power. And then I can just subtract 1 to get r. And if I want, I can put that value of r into the model, or I can find a decimal approximation for it. And I will go ahead and find that decimal approximation. I'll use Wolfram Alpha to get that number. You can use any calculator that can handle exponents to calculate r here. It comes out to 0.0636. And just note that's about 6.36% per year. That's about how fast, not per year, per day. That's about how fast the number of views is growing per day. So that's some pretty intense exponential growth. Now we're just going to go back and put that number into the model. And then we also need to solve for A naught. We had the equation before. We had two different equations to solve for A naught. I'm going to use the first one. 15 over 1 plus r to the 15th. Plug in the r. We can punch that into some calculator. When I put it into Wolfram Alpha, I get 5.949 for A naught. So notice this model is not accurate probably for the very beginning. When this video first came out, it's saying that you have 5.95 million views to start out with. It doesn't really make sense, but we can use this model to make predictions about how many views the video will have after 40 days. Now we're going to set up the model slightly differently, using A0 times e to the kt. That's because in calculus it's more convenient to analyze problems like this, exponential equations, if we use a base of e instead of a base of 1 plus r. The 1 plus r is more intuitive. The r makes sense. You know how fast the amount is growing. But let's go ahead and translate to k. We'll set it up just like we did before. We've got 2 data points, sets up 2 equations. We'll solve for A0 in both of those equations. And this will allow us to solve for k, and then we'll go back and plug in what k is to find A0. But I want to point out that we could just use the fact that k is equal to natural log of 1 plus r. And I've shown why that's true in another video. It's fairly quick and easy to follow, so you can look at that if you would like to see why. But we could use that equation. I'm going to go ahead and work it out the long way. If I divide both sides of that top equation by e to the 15k, that gives me 15 times e to the negative 15k. Do the same thing with the second equation. So I get 70e to the negative 40k. And then I want to set those 2 equations equal to each other. The right sides have to both be equal because they're both equal to A0. Instead of writing e to the negative 15k, I'm just going to put it, move it down to the bottom since the exponent is negative. So I get e to the positive 15k in the denominator on the left, e to the 40k on the right. Multiply both sides of the equation by e to the 40k. And then our goal, remember, is to solve for k, so I'm going to divide both sides by 15. That will allow me to just have e to the 25k on the left. And from there, I'll be able to change it into a logarithmic equation. And if I want, I can punch it into a calculator. So take the natural log of both sides, or just rewrite it as a logarithmic equation. Log base e, remember, we write as natural log. So we get natural log of 14 over 3 is 25k. Divide both sides by 25. And then we can put this into a calculator if we want to get a decimal approximation. I will go ahead and do that. When I put this in the calculator, I get 0.0616. Notice that's really close to what we got for r. And I've mentioned before that there's a good reason from calculus for why r is really close to k. The bigger r gets, the more different it will be from k, but they're going to be really similar for low values like this. So now we can go back and solve for A0 by plugging in k. I'll just plug it into the 15 over e to the 15k equation. That gives us our model.